My name is Michael Pagel, Program Manager of Greening Healthcare, and I'd like to welcome you to today's webinar. Our topic today is low carbon planning. We'll be presenting case studies and discussion around low carbon equipment replacement options such as heat recovery chillers, enthalpy wheels, and adiabatic humidification systems. This is looking at replacements on existing buildings rather than designs of new buildings where a lot of these systems are already in place. And also, if you missed our webinar, just a reminder, it was on March 5th about recommissioning. Be sure to check out the site on greeninghc.com under events, since energy efficiency should be kind of the first step that you look at in your journey to net zero emissions. Greening Healthcare is a program of the Climate Challenge Network with technical direction from Enerlife and a partner with CHES. We're funded in part by the Government of Canada through the Implementation Readiness Fund. And a reminder, ask any questions you might have through the Q&A, and we'll try to answer those as they come in. And then the next slide, just a thank you to our program sponsors, which include Belimo, Blackstone, Ecosystem, who's also sponsoring this webinar, Elliston Facility Services, Enbridge, PCL Construction, Smith & Anderson, Thermogenics, and TMP. And a special thank you to Johnson Controls for sponsoring this webinar. And with that, I'll turn it over to Ian Jarvis, the Executive Director of the Climate Challenge Network, to start us off with the land acknowledgement.
Thank you, Michael, and hello, everybody. As you know, with every Climate Challenge Network event, we begin with the land acknowledgement, where we do acknowledge with respect the ancestral and unceded territory of Inuit, Métis, and First Nations people that share these lands with us. We're meeting today on a virtual platform, and we have audience members today from across North America. So you're all on different traditional homes of different First Nations people. I'm speaking from Toronto, which is the traditional home of a number of nations, the Huron-Wendat, the Haudenosaunee, the Anishinaabe, and the Mississaugas of the Credit River. And you may know that Toronto, the Toronto Purchase Agreement was known as Treaty 34 with the Mississaugas of the Credit River. Again, as always, it's our sincere hope that the work we're doing, the work we're sharing with you today, and the work that you're doing in your different parts of North America are all contributing in a meaningful way to our common responsibility as stewards of the environment. A quick look at where we're going with this. Amandeep is going to be leading most of this session because it gets beyond my technical grade in a number of these areas. So looking forward to Amandeep and his panelists sharing specific information which we hope will be useful to you. I wanted to provide a bit of context around the energy transition. It's well underway. Talk a little bit about where we came from, where we're at right now, and where we need to go. We picked three of the technologies which we hear most from Greening Healthcare members about, and which we believe are going to be major parts of your low carbon future. Every hospital on this call is in some state of transition. Some are further advanced than others, but over time and fairly quickly, we're going to be moving to a decarbonization scenario. And exhaust air heat recovery, pulling the heat out of the exhaust air before it leaves the building. The recent adoption in Canada of adiabatic humidification using evaporation rather than steam, and heat recovery chillers. Those are going to be the primary focus for today's work. And as always, we try to present you with the theory, if you like, the facts you need to know about the technology, what it looks like, what it weighs, how it works, how efficient it is. But it always comes to life when we've got real live examples of folks that are already taken on this kind of work. And we're all endlessly grateful to the time our panelists, our case studies, folk put in, both from Island Health and from Lakeridge Health in Oshawa today. And then at the end, we'll talk a little bit about next steps. How does everybody align themselves with the realities of the low carbon future and get started, because time is not our friend with all of this. So that's our plan for the day. Next slide, please. So let's run briefly through how do we get to this state. And you've seen this picture before, but it's worth reminding ourselves. So back in the 19th century, we relied primarily on wind and animal power. There are only 1.6 billion of us sharing the planet by the end of the of the uh, of the 19th century. We were already heavily into deforestation, so wood was our primary. Coal was around, but mostly we were deforesting the planet to provide wood, to provide steam engines, to provide all the things that were going on. But it was a simple world back in the 19th century. Then came the miracle of hydrocarbons, and we should acknowledge they were miraculous. The amount of punch that they pack into a cubic meter of gas, or a liter of gasoline, or gallons, or therms, if you're on the other side of the border, is quite remarkable and made so much of what we know today possible. So oil, natural gas, all fossil fuels. So the discovery of oil in Pennsylvania, actually in 1859, changed the world geopolitically, changed the world in terms of progress, enabled the lifestyle that we now enjoy. So we don't want to knock hydrocarbons, but here we are 200 years later, and a resource that took over 100 million years to produce. We burnt through as much of it as we can afford to use in less than 200 years. So today we're in the age of decarbonization, and no matter what happens politically or economically or from a technology standpoint, that is our world for the foreseeable future. We're in the age of decarbonization. We have to rapidly wean ourselves off that miracle of hydrocarbons. We've got to use them more efficiently, and over time we've got to phase them out. And now there's 8 billion of us, 5 times as many people as there were at the end of the 19th century. So there's 8 billion of us sharing through this. The global challenge, mentioned geopolitics, you see it everywhere, and it's going to keep playing out. Technology is going to be a major part of it. Economics, it all comes to decision making, and decision making at the national level, but importantly at the individual level. In hospitals, every one of us has the opportunity to make a really substantive difference. Hospitals are remarkably energy intensive, and we've talked previously about how in many ways the healthcare system's at the forefront, in the crosshairs of the whole climate crisis and the climate action. So that's where we are today, looking to manage that transition. And while electric vehicles and windmills are somewhat abstract, in hospitals, it's very real. So Amandeep, good timing, because let's think about what that transition looks like from each and every hospital's perspective. And we've updated this slide significantly. Things are progressing fairly fast, but life begins with all the building systems that are within a hospital right now. And the next slide, please, Amandeep. And we're familiar with conventional plants. We got exhaust fans that blow away conditioned air, often 24/7, and right through the heating season and right through the cooling season. We've got steam boilers, we've got hot water boilers, and sometimes those are working together. What is reality for us in almost every hospital is the chilled water system becomes, if you like, it's the heat transporter. The chilled water system on a year-round basis is the way that you'll be collecting heat from different parts of the hospital and moving it to heat recovery chillers, typically, to where it can be used. So the chilled water system takes on an all-year vital role. If we go across to the low carbon plant, so this is traditionally how we've done things, primarily with steam. Today, the world looks quite different. We've got heat recovery on exhaust air. We will have heat recovery on discharge wastewater leaving the hospital. Two of the areas we want to focus on today, adiabatic humidification. So that is going to replace, we think, low pressure steam as being the approach to humidifying one of the remaining large steam loads within the facility. We've got heat recovery chillers that we're going to focus on today, which In most cases, we'll tap into that chilled water distribution system, that transporter that's carrying heat around the hospital, and pump it up to a grade where we can use it to heat the hospital. In our view, perhaps the biggest single opportunity, and one where I would predict that within 20 years, every hospital on this call will have at least one heat recovery chiller serving them, and we'll hear today how that works. Then the loads that feed into that chilled water system at the bottom of this chart, water-cooled condensers, air-cooled condensers, so many places within hospitals where we reject heat right through the heating season, over time being able to pull that back and recover it. So we're in transition from the left side to the right side. It involves everybody, and it starts now. Next slide, please. So we'll be obviously posting this recording with all these slides, so you don't have to take too many notes. We'll be making this available to everybody who's on the call right now. But we got 3 slides that you've seen before. Again, we've updated all of this that speak to the alternatives when we're doing low carbon planning, when we're looking at end of life equipment and replacing not like for like, but replacing with low carbon alternatives to like for like. It means every capital project, there's a decision to be made to, are we going to reuse something like what we had before or do something different? So you see the runs through here in terms of the heating plant. We're going to be looking at upgrading heating systems so they can accept lower temperature water. We'll hear some of that today. We're looking at reducing peak heating demand as well as heating energy consumption through energy efficiency, which is still the vital first step. You've got to be efficient before you can decarbonize. Otherwise, it's just too costly to get the job done. We're going to be looking at air handling units, which reject conditioned air right through the heating season, right through the cooling season. What are the technologies and how do we actually incorporate those into existing hospitals? Next slide, please, Emily. And the rest of these are here for reference. And what Amandeep's going to be suggesting to you is every one of you coming out of this session is going to look at your capital plan for the next 5 or 10 years and see what, if any, of these equipments are in need of replacement over that period, and start planning now for the low carbon alternative to like for like, because again, that is the most cost effective way to get to the decarbonized future. The last of these looks at equipment, medical equipment needs to be water cooled because otherwise you can't get the heat out of it. So all of these decisions are going to involve other parts of the hospital, and they're in your court to feed this in. So again, we're going to be proposing every hospital should have a bit of a stepping stone like this. The baseline on the left-hand side here is the median acute care hospital in the Greening Healthcare database right now. It's running a little over 60 equivalent kilowatt hours per square foot per year, the breakdown between gas in yellow and the electric and the blue electricity. The energy efficiency targets that we've got to get to the top quartile in terms of energy efficiency takes you to that level, saving about 1/4 of current usage is typical. Then moving to the heat recovery chiller, which will be pulling the heat that right now you're rejecting through cooling towers or condensers. That gets you down further, and getting to 30 equivalent kilowatt hours per square foot per year, which is our next milestone, if you like. Those are the steps around exhaust heat recovery. Every hospital is different, but every hospital will follow these same principles, these same steps, with variations on a theme, depending on what kind of plant and equipment you've got. But getting from the baseline to this low carbon endpoint, that is the plan for the next 5 years to 2030, and then the next following 10 years to 2040, so on. So let me pass this over to Amandeep to lead us into the specifics of how do we get there from here. Thanks, Amandeep.
Thanks, Ian. Good afternoon, everyone, or good morning, depending on where you are. So let's talk about some of the aspects that Ian mentioned overall, includes the elements that are needed in terms of reducing or your path to low carbon over the next 5-10 years, depending upon your capital plan. So we'll start with exhaust heat recovery system. So today we are focusing on sort of the capital or the retrofit aspects of these systems. So this is a typical air handling unit that you see in a healthcare facility, and you could have a 25,000, 35,000 unit as well. But this is just one examples of what you currently see. And there could be projects right now that you're planning to do, replacing some of these air handling units um, that are getting replaced as we talk about. And generally, if there is no planning done on these systems, they get to be replaced with like for like. And you have a similar unit here where it's currently steam fed from a central plant, and it's going to get replaced with the steam humidifiers and heating and cooling coil to match like for like. Today's what we're trying to address is that is there a different alternative to these units that you can actually use and now which would help to not only be better in terms of the energy efficiency overall, but also reduce these emissions significantly. And thanks HTS for helping us with these selections. They've been uh, very helpful and generous in providing all this data to us. Now, if you are in that position that you're looking at replacing a similar unit, now what does that unit look like if you were to sort of replace that steam humidification with the adiabatic humidification? And this is what our typical unit of 15,000 CFM looks like. You will notice that there's two things that change with this unit. One is obviously the length of the unit increased, which is given that you need a more absorption length for adiabatic humidification, and also the weight of the unit increased as well because of the obvious reasons. So this unit is a selection where it not only recovers the heat with the enthalpy wheel, which is included in there, but also has an adiabatic humidification system along with it. So when you're considering there's obvious questions that we get asked around what happens to my existing unit? How much extra land do we have the space in the mechanical room to fit this unit? These kind of units, or could this be a standalone system? There are multiple configurations that are possible with these systems now these days. So we would highly recommend you to kind of work out all those options when you're planning for replacement of these units. Like for like is going to push you 10, 25 years behind in terms of meeting your sustainability goals. So considering all these options around what are the options on the table that you can use now, given that the CSA now allows us to consider adiabatic humidification as one of the means to replace these systems. So it is recommended to look at these options. Let me continue that. Here's just a quick comparison for in terms of the length, weight, and the cost for these systems. As you can notice, obviously the cost increases from a conventional unit because we're adding a adiabatic humidification and also adding enthalpy wheel. But overall, it provides you a better solution which reduces the overall emissions in your facility because now you're not relying on a steam. And also you're recovering the exhaust heat from the exhaust, which was previously not an option in your case. You're offsetting your natural gas consumption in your building by doing that. There are considerations to be made because the weight of the unit increases by almost 10,000 pounds if you compare based on the 15,000 units. And also the length of the unit also increases. So those are a few considerations you have to think about when you're looking at fitting this unit in your existing plant or existing mechanical space, and what are the options you have available. But this is just a one comparison against a typical system. We talked about sort of retrofitting these units and why enthalpy wheels are one of the important elements in those is because they not only help you sort of recover that waste heat exhaust or waste exhaust from the system or from the exhaust, but also help you lower your peak heating and peak cooling demands as well. So as an example of a 15,000 CFM unit, you could actually reduce your peak heating demand by almost 1.1 MBH per hour heating season. And then similarly on a cooling demand, you could reduce down your cooling demand by 45 tons for a 15,000 CFM unit. These are significant numbers when you consider how the peak demand is going to become more and more critical, not only from electricity side, but also from the gas side as well. As everybody's trying to cut down their overall consumption, the peak charges for electricity and for gas is going to be higher and higher in the next 5 to 10 years. So ensuring that you reduce or manage your peak load in the building both in the summer and the winter, the heat recovery wheel is going to be a key component in those. And also, this is one of the components where it helps you to reduce overall emissions in the building by recovering the waste heat. Another options where heat recovery or heat wheels are not optional because of the size constraints or the unit constraints is to consider the heat recovery coils. Heat recovery coils, obviously, as you know, they're less efficient than enthalpy wheels. However, they provide more flexibility in terms of recovering that heat and using that heat now with heat recovery chillers tied into them. In the past, they have been used just directly recovering the heat from the exhaust air and then put them back into the outside air coils where there are limitations on how often and how much heat you can recover because eventually your frost on the exhaust side coils is a limitation. However, with heat recovery chillers, that limitation is kind of removed because you're actually not putting directly anything into the outside air. You're actually putting all that heat back into the heat recovery chiller and then reusing that into the building through hot water loop systems. So another thing to consider and then we do have example today with Lake Ridge site that they've utilized this concept to further increase the heat recovery chiller load availability on their site. One of the things that usually come to discussions around existing mechanical rooms is that how can we retrofit an existing AHU with an enthalpy wheel or with an adiabatic systems if we don't have a space? We're trying to sort of put this idea out that there might be possible solutions that could be considered, which are outside the box currently around these systems. So one of the things you could consider is if you have generally when in a mechanical space, you have an exhaust on one side, an intake on the other side, and then you have AHU systems lined up with those plenums. And yes, it's possible that you may not have space to retrofit an existing unit with enthalpy wheel. However, considering a new makeup air unit, maybe at the roof of the penthouse, or there's a space in there that actually takes that heat away, takes that all the exhaust from those plenum area, and then take that heat from it, and then reuse or sort of reject that heat into an outside air plenum using a makeup air unit. And you could use that combination approach with a single unit. So rather than retrofitting each of these units, you can actually put one unit that takes all that exhaust and takes all that intake and condition that space. So again, these retrofits are going to become important for you, for your facility to be considered, where replacing the traditional unit or limitation of due to the size is not practical. So thinking this outside the box solutions will help you to make sure you have exhaust heat recovery embedded into your system and you're maximizing the use of it. This is just a comparison of sort of 3 scenarios looking at a gas-fired GTS unit or gas-fired unit and an electric steam and a dry fog or adiabatic systems. Their cost or annual operating cost across 3 scenarios when you have a 33% outside air, 100% outside air with enthalpy wheel, and 100% outside air with just humidification, no enthalpy wheel. And you can see that scenario 2 is the least cost scenario for different units is obviously because of the enthalpy wheels that making that impact, that is reducing the overall energy needed for the systems compared to the scenario 3 where it's no enthalpy wheel. And also you can notice that the GHG emissions for each of these systems, that the enthalpy, the dry fog system or adiabatic systems is the least GHG emissions producing systems compared to gas-fired or electric in most of these cases. Just to kind of note, I think this is based on a Toronto grid, and if you are in Alberta or any other grid that is still currently high emission electric grid, these numbers will be slightly different in your case. And so adiabatic systems in those scenarios might have a different sort of payback analysis and GHG emission analysis.
So more broadly, Amity, thinking of the audience here, New York likewise is a high carbon scenario. So every one of these needs to be customized to the specific jurisdiction and to the site, right?
Yeah, absolutely. Yeah, it's just a one scenario based on that we presented here. But again, the idea is to kind of run these analysis when you're doing your system selections or planning for your bigger projects to understand how the operating costs, your emissions are impacted by different systems. Let's talk about heat recovery chiller. This is another equipment that is being considered in addition to exhaust heat recovery that is going to be essential in making sure that your transitions to a low carbon is implemented in a way that you mostly relied on internally generated heat and reusing that before looking at producing any other source of energy through geothermal or through solar PV or any other source of energy. So the heat recovery chiller is going to become a key aspect. I have Robert Larson from JCI joining us on the technical side to help us with this. But one of the questions, Robert, thanks for joining us this afternoon. So one of the questions that we generally get asked with these heat recovery chillers, we understand it's an easy to be put in on a new construction because you can size your heating and cooling loops for the low temperatures. Whereas existing buildings, it gets complicated because most of your heating coils, your terminal units, all are sized for hot water loops, right? And then the solutions people are asking is, if we can't have a heat recovery chiller that produces hot water enough to feed those loads, then when the boiler loop starts to go at a higher temperatures, heat recovery chiller doesn't work, or at least the low temperature heat recovery chiller doesn't work. Maybe can you help us sort of explain what this unit, which is currently being used in one of your projects and which you're going to talk about at Lake Ridge, how is this different from the typical other units that we see in the market, which kind of produces around 130 to 140? And then I know there are probably different vendors out there that could probably meet some of these ranges as well. But maybe can you explain us like how this is a high lift unit helps with those scenarios?
Yeah, you bet. And thanks for having me. I'm in deep. Yeah, we were approached by Ecosystem saying that they are working on this design for the Lakeview project where they have an existing facility and they don't want to downgrade the entire hydronic heating system. And fortunately, we had the technology and the R&D in place where we right-sized our heat recovery heat pump chillers to serve that high temperature market. So you don't necessarily need to replace your heating coils, your piping, your pumps and everything. There is technology out there, and it's not just from us. There is technology out there that can provide high temperature heating up to 180 degrees Fahrenheit for those existing facilities. It requires, different thinking than the typical standard single pass centrifugal or low stage positive displacement machines. These are machines that are more so tailored for this type of application, not only in the compressor design, but also in the refrigerant and the refrigerant management side of how the vessels themselves are designed and built.
I think this is interesting. I think and can you maybe address, is this one of the first units that you guys are at least installing in Canada or North America?
Lakeview is one of the first. Sorry, Lake Ridge is one of the first, but there's several others currently on order and being delivered in Ontario and other parts of North America. And for this type of application, for heat recovery chillers, no, these have been around for a long time, and it's something that the technology exists. But as refrigerant policy changes have been affecting the entire industry, we sort of shifted our compressor designs to serve that requirement while also recognizing the market out there of existing facilities that don't have the budget to replace their entire hot water hydronic system, but want to utilize the existing simultaneous heating and cooling load within their facility. So that's where this came from.
Yeah, one of the things I noticed, Robert, on this as well is that the part load efficiency of 0.6 or 0.46 kilowatts per ton, it's getting close to, I mean, a centrifugal chiller just for producing a chilled water. Like it's not, I think those are even slightly better in those cases. But where I'm getting is that like with this sort of with these products, like in the past, what I noticed with the heat recovery chillers was that if you use them only for cooling purposes, they're not as efficient as a centrifugal chiller. However, I think seems like with that recent changes, we're getting close to that. These machines are getting more and more efficient.
It all comes down to the individual project. There are heat recovery machines out there that use multiple stages of compression, and when you're doing just conventional cooling, 44, 85, and you only need the cooling load, there's no heat rejection, you just want to dump the heat out to a cooling tower, you can have the same efficiencies as a standard centrifugal chiller. If you need to design for a different type of system, where you want to use a positive displacement machine, then yes, you might take a bit of a sacrifice on that standard cooling capacity. But typically, most heat recovery machines shouldn't be designed for your full year summer cooling load. And I think the biggest message to deliver to any existing facility is, if you want to take advantage of heat recovery, the important thing to do is to study and analyze your current building loads throughout the entire year. You don't want to waste your time, your resources in properly sizing your heat recovery machine for what you think is the biggest cooling load that you're going to have. We can have auxiliary cooling machines that can serve that space. You want to optimize your heat recovery machine the way this team did, with the simultaneous load hitting that peak point where there is maximum heating and cooling that can be exchanged between the two systems. So yes, if you're sizing your main cooling system to use the same machines as your heat recovery, you're going to be taking a bit of a loss. But if you have your loads studied and you have a good understanding and you have proper engineering up front, you can right size that system to run at peak performance and get COPs, simultaneous heating and cooling COPs of 4 or 5 plus COP, even higher. And then during the summer, when you need peak cooling, you can run your cooling only centrifugals or whatever your main chiller plant operates on with that 0.5 kilowatts per ton that you want to see.
Thanks, Robert. This is and we're looking forward to the data coming out of this project, because this is we have a lot of interest in, and a lot of other facilities have interest in the applications of these heat recovery or high lift heat recovery chillers in these existing facilities.
Definitely.
All right, let's continue, and I'm going to just introduce the panel for today's discussion. Ryan Galloway from Vancouver and Hanel joining us regarding their and explaining their existing retrofit of heat recovery chiller in their facility. Matt Cannon from Lake Ridge is going to give us his perspective on how is the whole project retrofitting in an existing 24/7 of hospitals is needs a lot of coordination, and we'll hear from him. And Darcy from Ecosystem is going to walk us through the Lake Ridge design and some of the challenges that they face. So let me start with Ryan with you. And can you, at a very high level, I'm going to run through the slides that you shared, so we'll go through them. But maybe just a very high level, quickly present your side of the story. Like, why did you guys thought about heat recovery chiller in your retrofitting in your building?
Yeah, thank you. So the first slide here is just to kind of introduce our scenario. We're in BC and we have a mandate to reduce by 2050 by 80% of our kind of current emissions. And so West Coast General was a maybe say pilot site for us, a site that we really prioritized. Back in 2017, we implemented a heat recovery chiller system with an estimated benefit of a 37% emission reduction. We did not get any of that benefit for this particular project. We had some issues and challenges with that, and those really became pronounced back in 2021 when we had a heat dome in BC, and the challenges of the system were also on the rejection side. So we weren't able to actually get heat out of our building. So we had a system that needed a lot of attention. And so we put in a capital submission to put in a new cooling tower to be able to help support the site in just purely being able to respond to future weather. Next slide, please. And so I had mentioned that there was an issue with the system and we weren't getting any of that benefit. And this is a diagram of the why. And so if you look at the schematic, this is the heat recovery chiller system that was implemented. It was a 6-module multi-stack. And the challenge in the picture you can see there with the hot water return and the hot water supply, those are the designed temperatures. And what wasn't incorporated in the design, this is a picture of a post retrofit, is the valve between the orange and the red lines. And so what was happening was, and we learned this through our process with a series of different consultants. I'm on the owner side, but we had learned that there was bidirectional flow happening. And what was happening is the 50-degree water was short circuiting. And instead of being that 30-degree water returning back into the system, it was 45 degrees. So we really had a major impediment, and it made sense why post retrofit we really weren't receiving the benefits. And this also then in turn made the ability to utilize the chillers at their capacity constrained. Next slide.
Ryan, quick question on this. How are you making sure for the projects that you're still going to be retrofitting with the new heat recovery chillers that this kind of design issues doesn't come up? Like, what's your lessons learned on that, and how are you implementing those for another projects?
That is a great question. We actually afterwards went and looked at a similarly designed system at our Royal Jubilee Hospital and found the same problem and implemented the same solution. And so for us, we have a in-house team of engineers and technicians that work towards reducing our energy use and associated greenhouse gas emissions. So that group, and it expands, like myself, I'm on the new construction side. So we're kind of like an in-house resource where we're developing standards and best practices so that we internally know what to look for when we're implementing another system. As well, we do things like this where we share so that others can kind of learn from these and participate in sessions like this to learn so that we can optimize our systems. We have, I think, 6 heat recovery systems, and we've had different stories with each of them. This one was probably the best example of like the value of optimization, but there's been lots of lessons learned in our various different systems. Yeah, is that okay? So
Yeah, thanks.
how we kind of ended up coming up with that issue, that challenge, and that resolution was through a process we called Low Carbon Resilience Roadmap, which is we had those targets and we had to come up with plans and kind of have that future vision for what our infrastructure needs to look like to align for that 80% emission reduction, that transition to fossil fuel. So we had this big collaboration process on all of our sites. West Coast General, we had multiple engineers helping us coming up with different concepts. And so that the identification of that issue was through that process. And that had led to about a 20 to 25% emission reduction, which brought us close to that initial anticipated savings. But another thing that came out of that process was the realization through the concept and as well vetting the airflows that we could actually expand the exhaust heat recoveries by adding in more heat reclaim coils. And so we had 3 heat recovery units on the top of West Coast General, and we maximized the ability to the spatial availability to put in more coils for rejection. And so that then created another 35% emission reduction on top of the 55%. And then just this last January, we've been working with our on-site technicians and our equipment supplier being trained for these multi-stack units around the operational set points. And so we had realized that there was a low temperature mode that we could enable for the heat recovery chillers that would allow us to operate at a lower set point. And when they were installed and commissioned, they were just put into standard mode. And so we had to go through a bit of a process there to verify that we had the right glycol mix for the system to be able to utilize this. But as soon as we had enabled that, we got a further 20% emission reduction to combine to almost what our kind of 2050 goal is within BC of a 80% emission reduction. And the story isn't really done for this site yet. We are still working on closing that gap. So it's a really successful case of getting a system that had the right design intentions and then working through an iterative collaborative process to be able to realize the benefit. Next slide, please. And so this is a visual of that January change, the most recent change. So this was really just, and this wasn't really something well understood, I think, by many of us, in that we had different modes available within the programming of these heat recovery chillers. As soon as we had switched into that low temperature mode, you can see the difference of heat output. So the output is on the left side of the axis, and then on the right side, you can see the various different temperatures for the entering and leaving of the condenser. But just to stick with the heat output, we're going from 600 kilowatts up to about 900 kilowatts just by switching into that lower temperature state of operation. So just really rough math, that's a almost 50% boost of capacity. And if you go to the next slide, you can see that. So in order to implement those heat reclaim coils, we had to shut down our heat recovery system. And unfortunately, that meant, unfortunately, it took a very long time. And so we had the red bars here are almost a full winter without operation of our heat recovery chiller system, because that's how long the system was down for in order to enable this. So that's kind of these, the large red bars there kind of give us a really good baseline to compare against. In May of 2024, we had implemented the heat reclaim coils. And so you can't necessarily see that because now we're starting to transition into summer state of operation, but you can see that benefit when you're looking at November of 2024 or December of 2024 in comparison. You'll see 50, 60% drop on those bars. But the recent change is actually a little bit hidden here because in February, the last call out there, February of 2025, that was actually a colder month than January. So if you're comparing, you would look at that February 2025 against the highest bar here, January 2024, to see how far we've come on this journey.
Yeah, no, thanks, Ryan. This is incredible, and I think those difference in the red bars when heat recovery chiller wasn't operational versus when it's operational, it's incredible, and that's the power of this equipment, and when you have it operationally working and it gives you the maximum benefit, and not only sort of the regular reduction, but it also helps with the peak reductions as well. Thanks, Rand. Stay put. I'll get back to
Thank
you
you.
as well. Let me now bring in Matt and Darcy into this. So maybe let me start with Matt, with you around this overall project and your approach to this. Like, this is one of the older hospitals, and you are still in a similar situations with like other existing hospitals where the infrastructure is old and you still have to do something with your capital projects. And you guys decided to go ahead and sort of start retrofitting a heat recovery chiller. Maybe can you give us a background at a high level? Um, how did this all initiated, and initial sort of pushbacks or risks that you were identified or were seeing as this project was in discussion with your senior management?
Yeah, absolutely. Thank you. So good afternoon, everybody. Matthew Cannon, Senior Director of Infrastructure and Capital Development with Lakeridge Health. Our project lead, Lakeridge Health Electrification and Decarbonization. Project lead started as a case study to create an application for low carbon economy funding. And so we, in conjunction with Ecosystem, we pursued low carbon economy funding after a business case was developed to identify what the potential savings could be at a very high level. And the business case was drafted and submitted. Once we received approval of the low carbon economy funding, we then took that approval and created a more robust initiative, which I then took to my senior leadership team, using the carbon tax and the forecasted carbon tax as sort of the high level and the easy sort of approval mechanism in terms of avoidance, but ultimately reducing our carbon output and being environmentally and sustainably responsible were sort of the mechanisms that were leveraged in this initiative in the onset. Some of the initial questions that we had were in line with the risks of the carbon tax going away, which is, in my opinion, neither here nor there, as we would have an avoided cost of natural gas as a result of the reductions, plus not having to pay the carbon tax could be used for the business case to support the capital expenditures. And so it then turned into a conversation of how realistic are these savings. And once I sort of provided that substantiation of the savings for this initiative, it received a lot of support from our board of trustees, and we were able to pursue this initiative further. Ecosystem won the RFP. It was an RFP that was created based on an output-based procurement initiative. So I have a target based on the Low Carbon Economy Fund application, and I have a deadline based on the Low Carbon Economy Fund application. And we created an RFP based around those two mechanisms. And while a heat recovery chiller and an off-peak electric boiler and some other, low-hanging fruit, LED retrofit, et cetera, are certainly measures that could be implemented, we left it up to the market and to innovation to come to me with solutions to achieve a carbon output reduction of 3,530 tons as per the Low Carbon Economy Fund application, and to complete it by March 31st, 2025. And so we received 3 fulsome engineered design solutions, ultimately proceeding with the Ecosystem design solution, which consisted of the heat recovery chiller, an off-peak electric boiler, and some LED lighting retrofit throughout the building, sort of a deferred maintenance opportunity for Scope 2 carbon emissions.
Thanks, man. Let me get back to you with. I have a specific questions around your facilities and engagement of your
Please.
clinical steps. Let me bring in Darcy here. Darcy, like you
Definitely.
guys um, looked at this and proposed solutions, and obviously we talked a bit about this heat recovery chiller. Do you want to sort of I mean, maybe I'll give you an opportunity to explain this to people on the line, and then we'll get into the next slide, which more talk about your approach for these projects and how did you accomplish one of the challenge things with this working in an existing building. So the concept of heat recovery chiller is that it not only provides you and hot water on one side, but it also provides you cold water as well. So if you put 100 kilowatt of energy into the heat recovery chillers, you get 250 kilowatts of cooling energy back into the building. And then you also get a hot water, which is being, or 350 kilowatt, which is being used as hot water in the building. So overall, you get a better COP, combined better COP than a traditional centrifugal chiller, because the application of this is to produce cold water and also to produce hot water, which is used in the building. So maybe you can walk us through the hydronic networks. Like, what was the challenges do you guys face with existing, or were they actually set up in a way that you could easily tie in your heat recovery chiller?
Yeah, so the system at Lake Ridge, like coming into an existing facility, Lake Ridge has plenty of cooling installed. They had 4,000 tons of existing chillers, kind of typical centrifugal chillers, and those chillers operate in the shoulder and summer seasons. And in the winter, they actually run kind of a free cooling heat rejection system, so circulating chilled water through the hospital, rejecting that heat to the outdoors without needing to run a chiller. And fortunately for this project, they also had an existing hot water network that was fed by steam from the gas-fired boilers and by some combined heat and power units at the hospital. And so the challenge here, or the opportunity here, was to add to their cooling capacity in the summer, and then to produce hot water they were already using to heat domestic hot water, terminal reheats, and other loads. And then in the winter to leverage the chilled water network to find additional cooling opportunities, heat recovery opportunities, exhaust being one of those, to provide base load for the heat recovery chiller to be utilized at full capacity year round, generating hot water at the efficiencies you kind of described on the previous slide.
Awesome. Let me continue to roll this, and then this is kind of a similar sort of a breakdown of what you've shown. So maybe can you walk us through this as well, and then we'll come back to the questions around how did you, or maybe you can address that. How did you add up more capacity for the heat recovery chiller?
Yeah, so I think like most typical hospitals, you have kind of two energy sources, natural gas and electricity. And in most scenarios, natural gas is, only being used to provide heat, to provide domestic hot water, and to provide humidification, as well as like sterilization loads. And then you have, a completely disconnected system, which is everything fed by electricity. So your ventilation systems, your plug loads, lighting, chiller plant to do the cooling, all of these, various electrical loads. And these two systems operate completely independently. At Lake Ridge, there's a cogen plant, so there's a bit of interconnection between electrical and natural gas, but generally they operate completely disconnected. And so a heat recovery chiller, I think on the next slide, is kind of an opportunity to tie the two together. So Robert earlier was mentioning kind of syncing up simultaneous heating and cooling loads, and that's kind of the job of the heat recovery chiller. So in this case, we were sizing a heat recovery chiller not for the summer cooling load, which is thousands of tons, but sizing it for the summer heating load, which was around 4 million BTUs, requiring about 200 to 250 tons of cooling input. So that was the starting point for the heat recovery chiller. And then the second challenge is finding ways to load it year round. And that's where opportunities like exhaust heat recovery or, recovering from MRI loads and these types of equipment loads can provide or generate the base load cooling year round to load the heat recovery chiller. And then just going into existing facilities, kind of the challenge is to understand how the two hydronic networks are functioning. I mean, Ryan gave a good example, for his hospital in Port Alberni, where it was a small kind of like, misunderstanding about the hydronic network that was, costing them savings ultimately, and a relatively simple fix, benefited the hospital immensely. So understanding how the hydronics networks are operating is pretty important to, adding a heat recovery chiller to an existing facility.
Thanks, Darcy. And then this additional expanded heat recovery was a result of tying into or installing new exhaust heat recovery coils in those exhaust systems, right? Maybe can you explain us, like, what was that process and how did you guys accomplish that?
Yeah, so we looked at a few different opportunities at Lake Ridge. We've done, heat wheels as you described earlier on other projects. We looked at that, but what we found at Lake Ridge was a good opportunity where there was a single large exhaust system with an existing recovery coil in it, connected to a runaround loop to some air handling units. There was a large imbalance in like the CFM and the exhaust and the units being fed. So, we understand that there's additional heat to recover as a result of that. And so tying into that system was a relatively simple way to expand heat recovery through the winter.
Did you guys
Unfortunately,
end up adding new coils for that whole system?
No, we did not. What we did was, so there was this runaround system was a glycol loop from exhaust to fresh air preheats, and
Okay.
we added a glycol to chilled water heat exchanger to this loop.
Okay.
So when the preheats do not need, the full recovery capacity of that exhaust, we divert glycol through a chilled water heat exchanger and bring that heat back to the heat recovery chiller through the existing chilled water network. So really, like, it's about, chilled water is going everywhere in a hospital that there's a ventilation system generally already. So leveraging that network to get the heat back to a heat recovery chiller is an efficient way to do a project like this.
Well, and typically we see, I think this is probably additional opportunity, and I'm going to come back to you, Matt, on this is that these are some of these sources that are available in your acute care hospital that generates that 24/7 load, right? From previous discussions, not all of them have been yet tapped in with your systems. Matt, how do you plan to expand this project to tap and rest of the sources that are out there to increase the load availability on the heat recovery chiller?
Yeah, so I think in looking at the heat recovery opportunities in what might be considered non-traditional heat sources within the facility, I think that is the next step in sort of our carbon reduction strategy for Lake Ridge Health, and certainly our diagnostic imaging program is probably our primary focus for the next stage of this initiative. We'll look into IT as well, with a very large server room at the Oshawa site and the need to keep that space conditioned. But I would say the MRI and the CT spaces, we have a large cancer center here as well. So there's a lot of opportunity that does exist with those heat generating pieces of equipment.
Yeah, thanks, Matt. I think it is a process because a lot of these equipments have a different end of life and they get replaced through different departments. The idea is to make sure that you have a plan for your facility to ensure that these water cooled loads doesn't get converted into air cooled, because then you lose the opportunity with
Precisely.
recovering those heats, right? So having them on with your FCAP and working with your clinical teams to make sure that these get tied in eventually is a key. So I'm gonna thanks everyone for your time, and we ran a couple of minutes over.
Sorry, Amandeep,
But
just quickly before you move on, I know that
sure,
we're
go
past
ahead.
time, but I think one thing that we should mention with respect to heat recovery chillers is turn down. I think when people think chillers, you expect that you can get, your standard 10% turn down like you've been getting on your conventional chilled system forever. Heat recovery systems don't have necessarily that same available turn down. The team at Ecosystem did a good job analyzing, okay, what is the available load during the winter months that I can actually reject the heat towards? And it's something that you need to understand when you're designing for heat recovery chiller systems. And then there are some comments about the adiabatic humidification. A good comment that someone brought up was about stainless steel requirements. CSA Z317.2 was recently updated to permit adiabatic humidification. However, there is some construction elements that you need to consider if you're installing that type of system. So just while I have the mic, I just want to make sure people are working with their trusted support networks to design it right into the code requirement. Thanks, Amandeep.
Thanks, Robert. Absolutely. These are all I mean, details and insights that we always appreciate. Ian, back to you.
Yeah, we'll be quick. Thanks everybody for hanging in there. We knew there was a lot of content here, and frankly, there's nothing from what has just transpired that I would have considered trimming. So thanks for hanging in there. This is, in our view, really important stuff. And particular thanks to you, Amandeep, and to your panel, Rob and Matt and Ryan and Darcy for sharing not just today, but in the prep for this meeting. Your knowledge and your generosity are noted and greatly appreciated. Very quickly, let's just go through the rest of 2025 for greening healthcare. We got our summer workshop coming up on the 16th of June. It's in person, and hoping to see a lot of people coming from across our friends in North America. We get a lot more done in person, rubbing shoulders, than we can ever do through webinars. So please put it in your calendar and be there if you can. It's at the community center right beside Markham Stouffville Hospital, which is one of our leaders in terms of some of the stuff that they're doing, and we'll be going through the specifics of energy efficiency there. We got our September webinar coming up, which is looking at what's working out there, what are the most successful, what are the most regularly impactful issues. October, we want to talk a bit about procurement because it's an issue. And again, the in-person 24th of November in Toronto at the Westin Harbour Castle Hotel is our annual forum. And again, plan to be there if you can. So much more happens again in person than we can ever accomplish through webinars. So that's our story to come. The final couple of slides, I think. If you're not a member, about half the hospitals on this call are not greening healthcare members right now. Please consider joining us. We can only do things by having people directly participating, sharing data, sharing knowledge, sharing information. And if you can contact Heather, you can reach us through greeninghc.com. But we flourish on the network effect. Every new hospital brings their own new insights and gets the benefit of everything that's gone before. And the bigger that network grows, the more effective we become. And finally, here we are. I'm Ian Jarvis, the Executive Director of Climate Challenge Network. Heather is our Director of Program Partnership Development. She's the direct content for new hospitals and industry players considering joining greening healthcare. Michael is our indefatigable program manager that pulls these things together, and Amandeep is our technical expert. And thanks to everybody for contributing today, and thanks to everybody for being here, and our very best wishes for your continuing journey towards decarbonization. Thank you.